Welcome to the study of the dynamics of motion. Forces and motion, no doubt, have a kind of cause and effect relationship. But what is a force? What is motion? And how to measure these forces? Answers to these questions are available in the 3 laws of motion advanced by Sir Isaac Newton. Besides defining and describing the properties of forces, these laws provide ways of measuring them. These topics are covered in 2 episodes. In this episode, you will learn about the concept of force, its various forms, and the first law of motion. Here is the first episode.
Forces are in action everywhere. It is force that makes objects move from one place to another. It is force that makes a ball fly. A change in its motion is also brought out by this force. It is the force of expanding hot gases that makes vehicles come alive. The chemical changes in muscles make them contract, producing a force required to lift or push objects. Thus, force is a kind of a push or a pull that begins or changes motion.
There are various kinds of forces in nature. These are gravitational force, electric force, strong force, and weak force. Let us briefly examine the nature of these forces. The most fundamental force of nature is a gravitational force present in all heavenly bodies like the earth. It is this force that makes all objects to fall towards the earth.
In fact, as the story goes, it was the fall of an apple that made Sir Isaac Newton formulate the law of universal gravitation in 1685. The law states that every object in the universe attracts every other object with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. The law is expressed as Fg equals gm1 m2 by r square. Here, Fg is the gravitational force. m1 and m2 are the masses of the objects 1 and 2. R is the distance between them. It is because of gravitational force that objects, when let free, fall downwards, planets go around the sun, stars are born, and galaxies are formed by the clustering of stars. In fact, it is gravitational attraction that gives all objects their weight.
The second force of nature is the electric force that exists between the positive and negative electric charges. It is this force that is responsible for the working of many devices such as the electric fans and motors. These positive and negative charges are present in all elements. The protons present in the nucleus are positively charged, and the electrons that revolve around the nucleus are negatively charged. Any imbalance in the charges produces an electric force. This phenomenon can be observed in a simple experiment of electrostatic effect.
In this glass rod and silk cloth, the electrons and protons are in a balanced state. As a result, when brought closer, there is neither attraction nor repulsion between the glass rod and the silk yarn. But when rubbed together, the silk, due to the action of friction, collects free electrons from the rod and becomes positively charged. Having become positively charged, the glass rod readily attracts the negatively charged silk yarn.
Therefore, All electric forces are attractive between opposite charges and repulsive between like charges. A manifestation of electric forces is a magnetic force which exhibits the properties of attraction or repulsion.
For instance, this conductor connected to an electric source has an electric force having the properties of a magnetic field. It is this electric force present in the conductor that deflects the magnetic needle of the compass. A similar deflection can be noticed when a magnet is brought closer to the compass. This indicates that magnetic force is similar to the electric force.
The gravitational forces and the electromagnetic forces are macroscopic phenomena which can be observed without difficulty. But the other two fundamental forces, namely the strong force and the weak force, operate at the subatomic level.
The strong force and the weak force are known to be present in atoms. It is the strong force that binds together the protons and neutrons present in the nucleus. The weak force, on the other hand, is responsible for the beta decay process, in which a neutron decays to a proton, an electron, and an anti-neutrino.
Having examined the four manifestations of forces, let us now learn about the three specifications of forces. These are the magnitude, the point of application, and the direction. A study of these specifications is essential for a fuller understanding of the nature and operation of forces. All the three specifications are present in this setup, consisting of a sphere of weight W attached to one end of the string. The other end is fixed at a point so as to make it hang freely. Let us examine the three specifications of forces in this setup. The sphere is joined to the string at point B. The other end of the string is fixed at point A. The sphere pulls on the string with a force equal to its weight. The magnitude of the force here is the weight of the sphere, which is 134 grams. The point of application of force acting upon a body is that point at which the force is assumed to be concentrated. In this example, the point of application of force is located at B, where the sphere and the string are joined together. It must, however, be remembered that force is not concentrated on a point, but is distributed throughout the mass of a given object. But for the sake of convenience, it is assumed to be concentrated at a single point. The direction of force is the direction along a straight line through the point of application in which force tends to move a body. In our setup, the gravity force, that is the weight of sphere, acts vertically downwards. Thus, the direction of force is in the line of string represented by AB. Force is a vector quantity, for it possesses both magnitude and direction. In our example, the straight line segment BC represents the vector. This segment has the magnitude of the force represented by W and the direction of the force indicated by an arrow on the line segment BC. This implies that certain amount of force is acting from B towards C.
Objects are set into motion whenever a sufficient force is applied to them. The path of motion could be either rectilinear or curvilinear. In rectilinear motion, the objects move in uniform motion in the same direction. In curvilinear motion, on the other hand, objects move in a circular path. Our understanding of motion is not what it was in ancient times. For centuries, it was Aristotle's idea about motion that was widely believed in. According to the Aristotelian concept, a constant force is required to keep a body moving with constant velocity. Moving objects travel a short distance on rough surfaces having extreme friction. Rightly, Galileo pointed out that this change in velocity of a body moving along a horizontal plane is due to frictional forces and air resistance. On surfaces having relatively less friction, the moving objects travel a relatively longer distance. When the action of the frictional forces and air resistance are entirely eliminated, the body will move perpetually with a constant velocity along a straight line. Though such a situation doesn't exist in real life, Galileo reasoned that objects moving with uniform velocity would maintain the state of motion forever in the absence of opposing forces such as friction and air resistance. This property is known as inertia. It is this inertia that makes objects remain at rest when no force acts upon them. Galileo's concept of inertia was the basis for investigations by Sir Isaac Newton, who gave the three fundamental laws of motion. Newton's first law of motion, which is a reformulation of Galileo's concept of inertia, states that every body continues to be in its state of rest or in a state of uniform motion in a straight line, unless it is compelled to change that state by external forces.
In Newton's first law of motion, there are two parts. The first part of the law states that an object continues to remain at rest until it is acted upon by an external force. The phenomenon is commonplace. All objects at rest will continue to remain at rest until it is moved by the application of force. The second part states that an object moving with uniform velocity will continue to move unless it is compelled to change its state of uniform motion by an external force. From these two parts, it follows that a change in the state of rest or of uniform motion of objects can be brought about only with the use of force. Thus, force can be defined as an external agency that changes or tends to change the state of rest or of uniform motion of a body in a straight line.
Newton's first law of motion is in action everywhere. Flying objects keep moving until something either stops them or changes their motion in some way. This is why the planets which were set in motion when the solar system was formed continue to move through space. They are in a perpetual state of motion because there is nothing to stop them. Here is another instance of Newton's first law of motion in operation. A moving vehicle along with passengers is in a state of motion. For the vehicle to stop, a force has to be applied. When the brakes are applied suddenly, it is the motion of the vehicle that gets arrested, not the motion of the passengers. Therefore, the passengers are jerked forward. Here is a situation where both the postcard and the coin are at rest. When a force is applied to the card, it is the card that goes into motion, but not the coin. Not having come under the influence of force, the coin has to be in a state of rest, but it has lost its support. Therefore, it has to fall down.
These are just two examples. There are umpteen situations where you can observe the principles of the first law of motion in action. Examine those situations and explain them. That would help you grasp the essence of Newton's first law of motion. We will examine the remaining two laws in the next episode. Until then, read the books suggested here and answer the questions.
Besides your own textbooks, also read the book suggested here. Principles of Physics by N. Subramaniam and Brij Lal. Published by S. Chand and Co. Limited, New Delhi, 1990. Physics textbook by Arvind Kumar, B.K. Sharma, P.C. Jain and others. Published by the National Council of Educational Research and Training, New Delhi, 2002. Pradeep's Fundamental Physics by K.L. Gomber and K.L. Gogia. Published by Pradeep Publications, Jalandhar, 2003. Engineering Mechanics by S. Timoshenko and D.H. Young. Published by McGraw-Hill, New Delhi, 1956. Here are the questions for you to answer. Define force. What are the major classifications of forces? Define each of these and compare the magnitude of their strength. What is the force that acts between the planets? Why is gravitational force always attractive? What are the specifications of force? Differentiate the terms mass and weight. How does Newton's first law of motion imply that the state of an object at rest is the same as that of an object in uniform motion?
And watch the second episode of the Laws of Motion without fail. Until then, take care.
If you have any doubts to clarify, or if you wish to watch the unit again, write to the Director, Consortium for Educational Communication, NSC Campus, Aruna Asaf Ali Marg, New Delhi 110067, or email at cec@del.bsnl.net.in. You can also write to the Director, Educational Multimedia Research Center, University of Calicut, Calicut University, PO 673635. Email ID is mmrccalicut@yahoo.co.in.